This is a nice review, right? A lot of you seem to be picking this up pretty well. As always, the solutions to the group work, they are in Canvas. So as you're going back over things again, if you come across this and want to review it again, the answers are always there. And you also can talk to me as much as you need to about any of these problems. But that's really what I'm seeing, a lot of good work as I look around the room today. So great job on that. What I'd like to do next is come back to the chapter 5 material, which we had been working on these last couple of classes. This is all about inner product spaces. I put a recap on the board here. I think some of you might have already had a chance to jot this one down. It's just a summary of what we did on Tuesday. And I'm going to quickly go over that summary, and then I'm going to jump into helping talk about some of the homework problems from this assignment that is due tonight. Okay, and then in the later part of the class, I'm actually going to cover that first section of chapter 6 and also talk a little bit about what's going to happen next week. So we have a lot to do still today. But yeah, we were talking on Tuesday about how we can take any set of vectors whatsoever up here. So say V1 through Vn, a lot of times this might just be a basis for some vector space, right? And so if you start with a basis for a vector space, the objective, at least if you have an inner product in your sights, and if you're focused on the geometry of your vector space, your objective with those vectors may very well be that you would like to orthogonalize those vectors. Okay, guys, this material that's on the board here is not conceptually that difficult. You just need to know when to do what. So if you see a question that says, find me an orthogonal basis for something, right? That probably means you're supposed to follow this roadmap right here and orthogonalize the vectors. And we talked about this Gram-Schmidt process, which I'll remind you in a second. Yeah, Matt.
So when if I ask to find an orthogonal basis, then you have to find the basis for those vectors first, or make sure that's a basis first.
Unless they give it to you as a basis, they could say, here's a basis.
Okay.
Give me an orthogonal basis for it. Yeah, but yeah, you're absolutely right. Before you can, get an orthogonal basis for something, you have to make sure you have a basis in the first place. If it's not a basis in the first place, you're not going to be able to orthogonalize it into a basis. So yeah, so we're presumably we're starting with a basis. Maybe I should write that down. So this is any basis right here for whatever my vector space is. Okay, and then what we're going to do is orthogonalize it. And if we do that, then we get, of course, an orthogonal basis out of that process. Okay, and this is called the Gram-Schmidt process. I've listed here the first 3 formulas for the W1, W2, and W3 of the orthogonal basis that you end up with. Remember, guys, on Tuesday, I promised you that I would never ask you for more than 3. So, and I also promised you that these 3 formulas will be provided to you. So again, what I'm saying here, guys, is this is not that difficult because I'm going to give you the formulas. It's all just plug and chug, crunching the numbers. The main thing you have to just be careful with is that you watch out for those words. Find an orthogonal basis, right? If you see that and you write Gram-Schmidt process on your paper and you don't do anything else, I can still give you credit for recognizing what you're supposed to do, right? So be sure to make that association. Orthogonal basis is connected with Gram-Schmidt process, right? They go hand in hand, right? And it might be that not only do I want you to give me a basis that is orthogonal, I might be even pickier and ask you to normalize those vectors also. So this is where we take our orthogonal vectors. We had to do some of this in tonight's homework, right? Take those orthogonal vectors and just normalize them. This just means we divide each vector by its norm, right? So we divide each one of these vectors by its norm. It turns it into a unit vector. it still preserves the orthogonality, right? So the orthogonal nature that you have with these W's, if all I'm doing is stretching and shrinking those vectors, but I'm not turning them at all, then they're still going to stay orthogonal to each other. But in addition to that, they now will have a length of 1. And so they become what's called an orthonormal basis, right? So what I just wanted to emphasize here, guys, is that the word orthogonal and the word orthonormal, they sort of sound and look almost the same, right? So if you're reading a question, just read real carefully. Are they, because I don't want you to waste time normalizing a set of vectors if all they wanted you to do was provide an orthogonal set, right? Then you're doing more work than you need to. So just read real carefully these questions. I almost think that that's half the battle. Once you realize that, oh, he wants me to find an orthogonal basis, that means I need to use the Gram-Schmidt process. Let me look up the formulas and just start crunching away, right? That's basically what it's going to come down to. Okay, questions on this? It's just a little summary of what we did on Tuesday. I sent you a link to watch a short video. Did anybody have a chance to do that? You guys watch that little video? It's only 9 minutes long. It's got a couple of examples of the Gram-Schmidt process. So if you haven't done that, and if you're kind of stumbling through the homework out of 5.3, you could certainly watch those examples. They're not hard examples. I just wanted to sort of show how the process works. Well, it looks like I'm going to get to do that today anyway, since the problems are on the board over here. But yeah, so feel free to watch the Gram-Schmidt process videos. It's a little a couple people have been coming by my office. They've been saying, yeah, chapter 5 seems easier than chapter 4, but it's just tedious. And actually, that's exactly how I would describe it as well. It's mostly just tedious. It's not that it's like conceptually like some crazy ideas. It's a little bit, because you have these norms, right? The norm, as you remember, has a square root in it. So now you've got these radicals flying all over the place in the calculations. So it's a little bit messy, but it's really not that bad. So let's take a few minutes here, guys, before we take our break today. And let me help you with some of these homework problems. Does that sound like a good time to do that? We'll do that next. And thank you so much. I know I had you do homework like 3 times this week. I hate doing that. I try to keep them small so that we're not overloading you too much, but I just needed to have you get all this done so that we're ready to study for the test next week. And I think we're in great shape for that. So I'll help you with these problems. Let's look at number 6. These are the same ones that people have been asking me about. By the way, I really appreciate a lot of people coming to my office hours also. That is great. Just feel free to continue doing that, both in person and in Zoom. Definitely around a lot, and I want everybody to do well. So just let me know how I can help. But right now I'm going to help with some of these homework problems. So let's take V, which is the vector 7, -2. And it just says determine all non-zero vectors. So I need to find W. And we don't know what W is yet. So what I'm going to recommend, guys, is that we make a vector out of that has general variables in it. So let's just call those variables maybe A and B. And it just says, find all W vectors such that the goal is here that V and W, V comma W, is orthogonal. They just want the 2 vectors to be orthogonal. And can somebody remind me, in the world of R2, if I want to know if 2 vectors are orthogonal or not, how do I test that? Vanessa? Their dot product is 0. I couldn't have said it better myself. Exactly. We just dot those 2 vectors together and we should get 0. So let's just write that down. Whoops, not 0 vector. The 0 number is equal to the dot product, which is in general just the inner product. Remember, it's really the same thing. And in this case, if I just do the dot product of V with W, just using my regular dot product process, I should just get 7A minus 2B. Okay. And again, we're setting this equal to 0 because we want the vectors to be orthogonal. Stop me if there's any questions on this. Okay, so you can see that there's going to be lots of choices for A and B. And in fact, if I want, let me just put the 0 over here as well. If I wanted to, I could just imagine B as a free variable, right? I can actually choose any number for B that I want, and then solve for A in terms of that free variable. In this case, if I solve this for A, pretty easy to do this. We just have this one equation to play with. It should just be 2/7 times B. Okay, great. So if B is equal to T, well, then A would be 2/7 of T. Okay. Isn't it amazing? We're still like doing all of the chapter 2 stuff. We're like setting up free variables, solving it by back substitution. Right, that stuff just doesn't go away in this class. Right, up to the very end, we're still going to be doing it. So yeah, so we have basically 2 slots here. So what's my answer for W? W should be 2/7 of T, comma, T. And T is just any real number. And so this would be a perfectly good answer. You just put that in a box and call that good. I know it says in the question that they want to find all non-zero vectors. If I want to find a non-zero vector, then I just have to choose T not to be 0. So that hardly needs to even be mentioned. Does it make sense? This is a common thing that comes up in engineering, right? You have some vectors in your hands already, such as V, and you would like to supplement that vector or vectors with some additional vectors in order to fill out a basis for something, right? So unfortunately, it would be nice if the only basis we ever had to look at was 1, 0, 0, 1. But it doesn't work that way. In engineering, we have lots of situations where, you know, your cranes and your ropes and your pulleys and stuff, or they're not pointing in the 1, 0 and 0, 1 direction, they're pointing in some other direction. So you have some other vector in your hands, and we have to live with that vector. We have to live with V. We don't get to change it, but what we want to do then is try to supplement it with some other nice vectors. So in this case, we could find an orthogonal vector exactly as I've just shown you here. Okay, so that's kind of number 6. Any questions on that one? Yeah, go ahead, Brian.
Why is B a free variable?
It's just because actually, if I thought of this one equation as a matrix, I could put it into a matrix just like this. And it only has 1 row because there's only 1 equation, and my pivot would literally follow the first position. And so my second variable, which is the second column, does not have a pivot. So it's free. That makes sense. Anything else on that one? Okay, the next problem, number 7, it kind of takes this up a notch. Instead of trying to work with vectors in R2, they're going to give you vectors in R3, or they're going to give you 1 vector in R3 and ask you to fill it out to a basis. So let's take a look at I like number 7. It's a good problem. Again, it has great applications. So try to give you some good applications here. So number 7, this time they give you the vector -3, 6, and 1. And they want you to make an orthogonal basis for R3. So find orthogonal basis for R3 this time. So how many additional vectors would I need if I want to have a basis for R3? 2 more vectors, right? Because the total basis for R3 should be 3 vectors in it. They gave us 1 vector that we have to live with. This was, for whatever reason, the vector that our problem gave us. We have to keep that vector. We would like to supplement that vector with 2 more vectors. Now I can do the same approach. I can start off with W equals ABC, right? And I can once again take the inner product of V with W. Let's just see how this is going to look. I'm just going to do the dot product of V and W. This time, I'm going to get a negative 3a plus 6b plus c. And again, I'm going to set that equal to 0. Okay. And well, this time I actually have two free variables, which would be the b and the c. So I could, start working it out with the free variables that way. So I could let b equal r and c equal t. These are free. And then I could back substitute in and solve for a. Let me just see if I can do that in my head. I think it's going to be, if I move the 3a to the right side and then divide through by 3, it should be 2b plus c over 3, which becomes 2r plus t over 3. And so my w vector then, my w vector would become 2r plus t over 3, comma, r, comma, t. And this would be where r and t are real numbers. So just following the same process from problem 6, we're doing that now in problem 7, but this time we have two free variables. That's reassuring in a way because I'm expecting I need to come up with two more vectors, right? So if I actually wanted to specify some vectors here, I would have to choose numbers for r and t, or if you prefer, you could do what we were doing in the group work, which is to just bust out the variables here, right? So I bust out the r, for example, I get 2, 1, 0. I can see that that is orthogonal to v, right? If you dot negative 3, 6, 1 with 2, 1, 0, you get 0, right? So this is a good vector, but then I also have t. And when I bust out the t, I get 1/3, comma 0, comma 1. And again, we could we could dot that 1/3, 0, 1 with the original vector v, and it is orthogonal to v. Okay, so I'm trying to come up with my orthogonal basis here, guys, and I feel like we're close, but we're actually not quite as close as we might think we are. So let's be careful with this. Give myself a little more room here for this one. So we're supposed to come up with an orthogonal basis, right? Orthogonal basis. And we're supposed to definitely use v. So I'm going to put that in the set already because I know that they told us we're supposed to use that vector for sure. So can I then just grab these two vectors and make those my second and third basis vectors over there? What's wrong with taking those two vectors as my second and third vectors, Nick?
Their dot product doesn't equal 0.
Okay, exactly. Guys, each of these vectors individually is orthogonal to v, but they're not orthogonal to each other, right? This is the problem. So I can keep one of those vectors. Let's just take the first one. I can go ahead and use that one. I don't mind that, 2, 1, 0. And that one is orthogonal to the first vector v. So you just do the dot product, it does give you 0. But the problem is I cannot take this third vector. Because this third vector, if you dot the third vector with v, you're fine. But if you dot the third vector with the second vector, it doesn't work, right? 2/3 plus 0 plus 0. It does not cancel out, right? So the third vector would not be orthogonal to the second one. For an orthogonal basis, every mutual pair of vectors have to be orthogonal. So what are we going to do to get a third vector that would be allowed in our basis?
Make it orthogonal.
Make it orthogonal. We could make the third vector orthogonal. How do we do that? The Gram-Schmidt process could be used to do that, right? You have two vectors here, guys, that are not orthogonal. How do we make vectors orthogonal to each other? Oh, we use the Gram-Schmidt process. That's exactly right. So we could do that. Okay, turns out I think I'm not going to do that, but we could do that. Why do I say I'm not going to do that? That's because I'm in section 5.2 of the book. In theory, the Gram-Schmidt process wasn't even discussed until the next section. So what in the world are they expecting here? Supposedly, we don't know the Gram-Schmidt process when we're doing this homework problem. So does anybody know another way? If I have two vectors and I want to make a third vector that's perpendicular to both of those two, I'm really asking you to think broad and far here. Does anybody, you were in my office, right? Did I tell you the answer to this?
I don't think so.
Okay, do you have an answer for me?
I think you have to take the cross product.
Yes, is that what you were gonna say?
No, but I'll go with that.
You'll go with that. Yes, I'm so excited. Thank you. And that is exactly right. If you remember from Calc 3, when you take the cross product of any two vectors, you'll get a vector that's perpendicular to both of those two vectors. It turns out that that is easier in this moment than doing the Gram-Schmidt process. So we could just take the cross product. Now remember, guys, cross product, it only works in R3, right? If we were sitting here with a bunch of polynomials right now, we wouldn't have a cross product option. We would have to use the Gram-Schmidt process, right? But we happen to be living in the world of R3 right now on this problem. So I could take the cross product. Does anybody remember how to do the cross product of two vectors? Did they teach it this way with I, J, and K like this?
Yeah.
Okay. You realize that this is really a determinant,
Yeah.
right? They may not say that in 250A, but this is just a determinant. You just put these vectors here, right? And you like cofactor expand, it's kind of a funky cofactor expansion along the I, J, K row, right? So the I, you take I times this little 2 by 2, which is 0 minus 1, right? 2 by 2 determinant 0 minus 1. That gives me -1 on the I slot. And then for the J slot, we get 0 minus 2, which is -2. But remember that there's a sign change when you expand along the cofactor, expand along a row or a column. Every other position has a sign change. So that -2 becomes a +2. And then finally, the K component would be -3 minus 12, this little 2 by 2 submatrix here, -3 minus 12, which is -15. And we should check just to make sure. So we're obtaining this one by using the cross product of first two vectors. Totally okay for you to do that. And we should just check it. 3 plus 12 minus 15. That looks good, right? And then the second and third one, -2 plus 2 plus 0. It adds up to 0. So we have 3 orthogonal vectors, the first of which was the original vector that they gave us. And now we added 2 more vectors. Is good enough? Does everybody understand? It's not the only right answer. It's not the only right answer. We could have chosen to write this one down as our second vector, right? And if we had done that, if we had put that in the second spot here, then of course doing the cross product would have given us something else over here. Doesn't mean that that's a wrong. Anytime they ask you to find a basis for something, there's lots of right answers, right? So checking back of book answers and stuff like that gets a little bit complicated because there can be lots of right answers, and the back of the book is probably only going to show you one of them. Yeah. What do you think? Does that seem okay to everybody? Yeah, Saka.
How come number two in the last vector is positive?
It's because there's a sign change here. When I do this, so I cross off this row and this column. So I have these 4 numbers. When I do the little 2 by 2 determinant on that, I get 0 minus 2, which is -2. But there's a sign change. If you remember back to chapter 3,
So it's
plus, minus, plus, remember this thing? With the signs as I go, if I expand along a row, I have to do sign changes on the positions that have those minus signs. Yeah, man.
And so how do we know it was the basis again?
Well, so this is the right number of vectors, 3 vectors. And, technically, well, 3 mutually orthogonal vectors are for sure going to be Li. If you don't believe me, you can make a 3x3 matrix out of this and check the determinant is not 0.
Yeah.
But for sure, these are going to be Li, and you're right. I could have maybe said a little bit more about that here.
Okay.
But when vectors are orthogonal, then when they are mutually orthogonal to each other, you're not going to be able to make linear dependencies among them. So you're pretty safe on that.
Okay.
Yeah. Okay, anything else on this? Let's see, let's take a quick look at number 15. 15 is, I have to admit, it's a little intimidating when you first look at it because they put all this text in there explaining what's going on the problem, but actually most of the text that they write about number 15, this thing about Legendre polynomials, and then they put this scary looking differential equation there. We don't have to solve the differential equation, and we don't have to know what Legendre polynomials are. That's just a little bit of background. The main thing here is just on number 15, they give us 3 vectors. So these are functions this time. So f1, which is 1, f2, which is x, and f3, which is 1/2 of 3x squared minus 1. So they give us those 3 functions, and then they just ask us to show that these are orthogonal to each other. At least that's the first part of the question. Just show that these are orthogonal to each other. And the inner product that you're supposed to use here is, I'll just write it up here, the inner product of f and g. They give us the limits here. In this problem, they have limits from -1 to 1. So that has to be given. Remember, I talked about that on Tuesday. They have to give you this inner product formula. So that's what they've done here. And so we actually have to check that all of these are mutually orthogonal. So, for example, the inner product of f1 with f2, we have to calculate this. So this is just the integral from -1 to 1 of the product of the first 2 functions, 1 times x, which is just x dx. Right, so you're just integrating x dx, and of course that gives you 1/2 x squared when you do the antiderivative. We have to evaluate that antiderivative from -1 to 1. And it's pretty clear that you'll get the same value whether you plug in +1 or -1 because you're squaring it. And so the difference between the upper and lower limits is 0. You get the same thing. Okay, so you have that. We also have to do f1 with f3. So this is again, so we're going to be doing quite a few integrals here, guys, but they're mostly just easy integrals. The inner product of f1 with f3 is the integral from -1 to 1 of 1 times f3, which is 1/2 of 3x squared minus 1. And we can pull out the 1/2. And then we can do the antiderivative of the 3x squared minus 1, and I'll just get x cubed minus x. Again, I have to evaluate that from -1 to 1. And for both -1 and +1, x cubed is the same as x. 1 cubed equals 1, -1 cubed equals -1. They're just equal. So when you subtract them, you just get 0. Guys, you know what the answers are supposed to be. Right, you know it's supposed to be 0. If it's not coming out to 0, something's wrong. Okay, so you check that one, and then we have to check f2 with f3. Okay, so integral -1 to 1 of x times 1/2 3x squared minus 1 dx. This one's a little messier. I might take an extra step here. I'll pull out a 1/2, and then let me just simplify what's inside the parentheses. 3x cubed minus x, yeah? Hopefully I did that right. You just do one extra step on that one, and now I'm ready to go ahead and find my antiderivative again. So by the power rule, the antiderivative inside the parentheses would be 3/4 x to the fourth minus 1/2 x squared. This is from -1 to 1. And again, whatever you get by plugging in 1 for x will be the same as what you will get when you plug in -1 for x, because it's of even powers of x there. So when you, again, I would not spend a lot of time sweating that one. That's going to definitely equal 0. You can just kind of write that down. So these are mutually orthogonal vectors. And so this would be an orthogonal, set as a whole. The second part of this question asks you to then construct an orthonormal set. So in other words, to do the normalization part of it. So that is where we have to actually divide by the norms. We actually have to find the norms of these vectors now. It's a little bit more work than it looks like at first when you first read the question. It's a little bit more to it. So we actually have to figure out what is the norm of F1, for example. Okay. I might not do all of these. I'm just going to kind of get the idea going, and then you guys can finish this up later. But you just take the square root of the inner product of F1 with itself. Make sure you don't forget that radical that's on it. Okay, so we have the square root of, and then this is the integral from -1 to 1 of 1 times 1 times dx. So it's literally just dx here. And that comes out to be the square root of, well, it's x, which we evaluate from -1 to 1, which gives us 2. Okay, so the norm of the vector F1 is just radical 2. And so what we could do if we wanted to, we don't have to do this yet, but I'll go ahead and do it now anyway. We could make our unit vector, which is just the original F1 divided by the norm of F1, which is radical 2. So this is now the first vector that's going to be in my orthonormal set that I'm currently working on. Okay. Clear enough so far? Let's do the second one maybe. So the norm of F2, just to practice one more time here, and then I'll let you do the third one. Inner product of F2 with itself underneath that radical again. So here we have an integral from -1 to 1. X times x is actually x squared. So I have to integrate x squared dx. And again, easy integral to do. I just get 1/3 of x cubed evaluated from -1 to 1. And I plug in my upper limit and my lower limit, and I should end up with a 2/3 underneath that radical. Okay, so my second unit vector then, I'll call it U2. This would be F2 divided by the norm of F2. Right, F2 divided by the norm of F2. And of course, if I wanted, I could flip that fraction up to the numerator. I think in the back of the book, they flip that thing over. So it's radical 3/2 times x. Okay, so that's U2. And then U3, you just have to do one more time the norm of F3. So it's a little bit messier one, but I'm still going to let you do it. If you need to, you just multiply this out. 3x squared minus 1, you have to square that out 2 times. That'll get you to the answer.
We have to flip it or not?
No, you don't have to flip it. If you like to write it this way, in some ways, I actually like it this way better because I can see that you've got the norm on the bottom there. Yeah. So, yeah. So I'll let you guys finish the F3. I've done almost the whole problem right here. I'll let you guys check the norm of F3 and divide by that as well. Okay, great. Tell you what, let's take a break right now. I know we're not done with everything on the board over here. Let's take a short break for 10 minutes or so, and then we'll come back. I might do my 6.1 little spiel first, and then I'll come back and look at some of the 5.3 problems. That's kind of the game plan. for the rest of today, and then I'm also gonna talk about next week. Because there's been a little change on my side for next week, which is actually gonna be a good change, so. But let's take a break until about 3:17 or something like that. Take about 10 minutes to stretch your legs if you'd like.
Oh, yeah, it's.
What's going on? I did. And it worked out nicely. Yeah. Thanks.
I know. it.
I chose.
They wanna make a
cross point of.
Oh, okay.
Right.
That's-
I just
Don't say they're ignoring you.
I could brute force it to 0.
It's a problem right now.
More got the attention is to match that.
Oh, that's true.
And then like.
And then, but it does have to match, but does it match with the, oh, you chose
It's
the.
actually the same exact thing.
Ah, clever, yeah,
Yeah.
Aaron submitted it to ours.
It's exactly the same.
beautiful. Yes, that is very clever. I like that. Yeah, good job with that.
I'm not gonna do it again.
No, that's a neat idea. Yeah.
As a presentation. All right, I'll let them know. Wait, what are we submitting it to? This way, but onto the, which chat,
That's why on today's.
onto theirs.
This one,
Oh, okay.
and then. this project stuff.
Yeah, did you already put it there?
And everybody says she doesn't want it as a yeah.
Oh, okay. Oh, you don't know how to convert it.
Mhm.
All right. I didn't get you. Is the original file on the other chat?
Mhm.
Is that Aaron sent it, right? Well, it's like with Jacob, I get 6 and 7. Oh, I think it's like I do. How'd you know you saw? Wait, why are you gonna cancel it? Wait, when later? Yeah, I'm asking. In the morning, I think that's no?
All right, guys, I think I'm gonna go ahead and pick things back up here again. You guys look ready to go, so might do that. I just want to remind everybody, I think you know this by now, that we have a midterm coming up. I already went over the fact that there's a folder in Canvas with a bunch of resources in it. This midterm is next Thursday. And so of course it'll be here. Of course, you'll have the entire class period to work on it. It's going to cover, so that's 1019, exactly as scheduled in the syllabus. It's going to cover 4.1 through 4.10, except not 4.7. We did not cover 4.7. And then all of chapter 5, which we actually are pretty much done with now, except for maybe a couple homework problems, we're pretty much done with chapter 5. And then the thing I'm going to talk about right now, which is just the first section of chapter 6. So we're going to start talking about that in the rest of our class today. So this is what the exam is going to cover. I would estimate roughly that this chapter 4 stuff could easily be half of the exam. It's a pretty big chapter, 50%. And that might even be a little bit conservative on the estimate. Chapter 5 that we've been doing on inner product spaces might be, sorry, I meant to write 30% rough. This is roughly, I've not written the test yet, roughly 30%. And chapter 6.1, maybe about 20%, which is what we're just gonna cover now. And so that's kind of a breakdown of it. Of course, you can look in the folder, the resources folder for sample exams, a review packet, the review session, and I've got video for that as well. In the review packet, I actually realized I forgot to actually put the office hours down, what I'm gonna have for my extra office hours for the exam. So I'm going to sit down when the dust settles at the end of today, figure out what those are gonna be, and I'll add those to that handout, and I'll probably also email you guys what my hours are gonna be as we get closer to the exam. Now, that's next week on Thursday. Originally, I was supposed to be gone on Tuesday. I don't know if did I tell you that? Okay, I did tell you. It turns out my plans have changed. I'm not going to be gone on Tuesday. So scratch all of that. This is actually a good thing for you guys because we've actually pretty much covered everything anyway. So what we're going to be doing on Tuesday is essentially reviewing for the exam. I'm going to do it as a review set. There's not going to be a lot of new material. But what I am also going to do, so this is the homework, I think, number 13 that's due tonight. I had originally asked you to do homework number 14, which is just the material from this first part of chapter 6. I had originally scheduled that to be due on Sunday. But because I'm going to be here on Tuesday after all, and it's a good chance to ask questions on the homework, I'm actually going to extend this one to Tuesday. And that way, part of what we can do on Tuesday as part of our review for the midterm is we can answer questions on that assignment. Okay, so we'll do that on Tuesday. I'm also going to have an extra group work that we're going to be able to practice with on Tuesday. And we'll just kind of just take a breath and like get all this material under our belt. If there's anything I don't quite finish this afternoon today, I can always throw that in on Tuesday as well. So you guys have done a great job of working hard to get all this work done and watch those videos and everything we've been doing, that we are actually in really, really good shape as far as where we are in the class. And so I don't have any problem with spending a lot of time on Tuesday since I'm going to be here now doing a review for you. Okay, so we'll review, we'll do some homework, we'll do some group work, talk about the exam a little bit. I think that might be helpful. Okay, does everybody understand the new game plan now? And as I said, I have to now refigure out my office hours as well, and I haven't quite gotten that piece done yet, but I'll send out an email with an update on that shortly. So, okay, great. So that's the plan. What I'd like to do, there's sort of two things left on the agenda here. I'd like to start with a little talk about the beginning of chapter 6, and I'll try to save just a little bit of time to maybe look at some of that 5.3 stuff. If I don't get a chance to do all of this, you guys are going to have to forgive me and maybe just stop by my office hours or shoot me an email with questions later today if you need to. Okay. But I would like to at least get this section started. This is about something called linear transformations. And essentially, guys, up until this point in this class, when we have had a vector space in front of us to look at, it has been one vector space at a time. So on one problem, I give you a world of matrices. On the next problem, I give you a world of polynomials. The next problem, I give you a world of vectors in Rn. And we play with all these different concepts sort of in one context or another. But we have never talked about relationships between these different vector spaces. Is there any connection between polynomials and matrices, or between vectors in Rn and calculus functions? Things like that. Can we make connections? Mathematicians are always trying to make connections. And so I wouldn't be bringing this up if there wasn't something to say about this, right? There is a very rich theory of relating one vector space to another, and it is done through the mechanism of a linear transformation. This is actually just a fancy word for functions between vector spaces. Let's write it down. I'm going to start right off with the definition here. We'll just kick things off. Start off chapter 6 with a definition. A linear transformation. A linear transformation is a function. I usually will use capital T for this function. So it is capital T. This is going to be my linear transformation. T is a function, it goes from V to W, and V and W, these are, of course, vector spaces. So I have two vector spaces in front of me now, V and W. Vector spaces V and W. So it is a function. Now, it's not just any old function. It's not just any old function where we have inputs and we have outputs, right? That's basically what I'm talking about. Inputs from one vector space, outputs from another. So I might be inputting polynomials and outputting matrices. Or I might be inputting matrices and outputting polynomials. Or I could be inputting vectors from Rn and outputting calculus functions, right? So there's like all possible combinations of inputs and outputs. So this is how we're going to be relating different vector spaces to each other. But it's not just a function. There is a very important requirement on a linear transformation that we also have to have. Namely, since a vector space involves addition and scalar multiplication, those two operations have to be somehow respected by this function, right? Namely, so let's write it here, two parts, A and B, right? The first one is T has to respect, T respects addition. I'm going to write down what that means. T respects addition. The way I can write that one is if I take T of, let's say, V1 plus V2. If I have V1 plus V2 and I want to apply the function to that, I want to take T of that. It should agree, it should be equal to what I would get if I separately transform the vectors alone and then add the results afterwards. So you see what's going on the left side, I add the vectors first and then transform them. On the right side, I transform them individually first, and then afterwards I add them together. Either way, I should get the same answer if T is going to respect that addition. Okay? And then also, you won't be surprised that part B here is that T should respect scalar multiplication. This is the other vector space operation, and T has to respect that one as well. How is that one going to look on paper? Well, if I have a scalar, which I usually like to call K, times, let's just say V1. So if I want to transform K times V1, then what this should mean is that if we would prefer, we can transform V1 first and then do the scalar multiplication by K. Okay, so this is what it means for T to respect addition and scalar multiplication. This is going to be for all scalars K. So K is an element of the real numbers. And V1 and V2, those are elements of V. This is what a linear transformation is. Okay. So maybe we'll write down an example. See if we can write down an example here of a linear transformation. Is everybody okay with the definition? Kind of makes sense? So it's a function at its core level, it's just a function, but it has to respect addition and scalar multiplication as well. Right, okay. So let's try an example. Let's define, this is a typical problem that I would ask you to do. I would give you a transformation, first of all, and then ask you, is it a linear transformation? So define T from M2 of R to the real numbers. So that, by the way, the real numbers is just like R1. Okay, so it's just one real number here. And I'm going to do this. Now, if I stop right now, I have not given you the formula yet. I've just told you what the inputs are going to look like and what the outputs are going to look like, but I have not explained how do I actually transform a specific 2 by 2 matrix. So I have to do that via So I have to plug in, let's say I'm gonna plug in a 2x2 matrix. I'll just say A, B, C, D right here. Okay, and then I have to come up with some kind of an output. Let's just say I'm going to do A minus B plus 5C. This would be an example of a formula that you could be given. So we're just making up an example. Notice I have an input that is a 2x2 matrix. I have an output that is just a number. Okay, so inputs and outputs. This is a function, but the question is, and here's what we're going to do. We are going to show that T is linear. Show that T is, when I say show that T is linear, that's just my shorthand of saying linear transformation. Okay, so I won't always just write out the word transformation every time. I'm just going to say show that T is linear. It means show that it respects addition and respects scalar multiplication. This is going to remind you a little bit of something from the beginning of chapter 4, when we had to like check that a subspace was closed under addition and closed under scalar multiplication. It was a two-part process that involved the two operations in the vector space. And this is the same thing. We have a two-step process here, two parts to it, that we're going to check with respect to the two operations of the vector space. So let's check it, okay? So for the solution, see if we can do this now. I'm just going to show that T respects addition. I'm going to start with this one. So this is going to be, so what do I have to do for addition? I have to take two vectors from V. So that would, in this example, that would be two 2x2 matrices. So it would look something like this. T, well, actually, so, yeah, no, this is fine. So just T of, and then we take a matrix, let's just say A, B, C, D. You can use whatever letters you want, guys. It's totally okay. And then on the other side, the other vector, maybe I use X, Y, Z, and W. Okay, so I'm going to do that. Okay, and just so everybody understands here, right, this first one is like the V1, the second one is like the V2. So you have like vector V1 and V2, you're going to add those together in the parentheses. Now, guys, I'm going to be a little, just like I was with the closure under addition and scalar multiplication, I was a little bit picky, like how we write it down carefully. I want to do this carefully as well. So the way I want you to do this, guys, is below this left-hand side here, this should just be empty. Right? I don't want to see people working on both the left and right side of a bunch of steps, because it's a mess, right? So let's keep this very organized. I'm going to start on the left here, but nothing else gets written below that. The rest of my steps are going to all happen over here. Okay, that's how I want this to lay out. So what do we do first here, guys? Just based on how the parentheses look. Do I add the matrices first? Or do I apply the transformation first? Inside the parentheses. Yeah, I'm adding the matrices together first. So let's just do that. I'm not applying the transformation yet. I'm just going to add these matrices. So A plus X, right? And then B plus Y, C plus Z, and D plus W. I'm just literally adding those two matrices together. Now, what I have now is a single matrix that I am ready to transform. And I have the formula for how to do the transformation of any matrix. So we're going to apply this formula to that matrix. What's the formula tell me to do? Upper left corner minus upper right corner plus 5 times lower left corner, right? Whatever the entries are, I take upper left minus upper right plus 5 times lower left. Let's do that. Upper left is A plus X minus upper right, which is B plus Y, plus 5 times lower left, which is C plus Z. So we just literally follow the steps that way. Now, sometimes people get a little bit tangled up in their mind about like, what are they supposed to do? Especially halfway through, it's a little bit like not simplified here. if you get lost, if you get kind of a little shaky on where you're going, it's not wrong to sort of jump to the punchline. I do know that by the time I get to the bottom of this work, I should have the two transformed vectors totally split apart from each other, right? That's the right-hand side of my first requirement here. So I need to end up eventually with T of ABCD added to T of XYZW. If I set that template up for myself, I sort of get a better idea what I'm going to try to do next, right? See, I can see that I want to get all of the ABCD stuff kind of in the front. And I want to get all of the XYZW stuff kind of moved to the back, right? So based on that, do you have an idea what I might want to do with this sort of messy looking alphabet soup of letters here on the second line? Separate it out, and how about we just like try to move all the A, B, C, D pieces to the front and all of the X, Y, Z, W stuff to the back, right? So I could look at this and say, oh, I see the A right here. I'm gonna jump over that X and subtract the B next. And then I'm gonna take the 5C because I want to put that in the front as well. I can kind of just grab all of those terms that have A, B, C, and D in them and kind of put them on the front end. Put them on the front end. And then everything that I skipped over, I now have to go back and put that on the back end. Right, so at the end, I would have now the X minus Y and plus 5Z. Just like that. By the way, in the real world, it doesn't always come out this smooth. I just happen to be in exactly the right spot now, where the first part of it is exactly T of ABCD, and the last part of it is exactly T of XYZW, according to the formula that was given. So we can just stop there and just kind of put a check mark like we do to confirm that T respects addition. Does that seem all right? Okay, great. The write-up here is very important. Right, we have to get the write-up kind of smooth, and this is what takes a little bit of practice. Let's, I have just a little space here to show that T respects the scalar multiplication. We'll do that part next. This is property B, right? So I have to transform K times my first vector. So this time, I'm going to start on the left with T of K times my first vector. So I just have a K there, and I multiply it by the matrix ABCD. And what do you suppose is the very first thing I'm going to do on the right-hand side? Distribute the K into each slot of this matrix. Yeah, so I'm going to write this as T of KA, KB, KC, KD. Right? We just throw the K through the whole matrix. That's how scalar multiplication works. Yeah, and by the way, again, I don't want to fumble around on the left side. So again, try not to see if you start messing around on both the left and the right side, then the algebra gets kind of hard to follow. It's a little bit, it confuses me. It might even confuse whoever's trying to write it down too. So it's best to just kind of work on one side of the equal sign. If you get lost, jump to the end. At the very end, you want to end up with the K on the outside. Okay. So that's ultimately what you want. You can see that right here. The K is going to end up on the outside if we do it right. So that's how I want it to eventually become. But let's take another step. I have a single matrix here that I'm ready to transform. The rule is upper left minus upper right plus 5 times lower left. Upper left, KA, minus upper right, which is KB, plus 5 times lower left. 5 times KC. Just go ahead and write that down. And what is this expression screaming at you to do next, do you think? You see here, you can factor the K out, right? There's a K in every single term. Let's factor it out. That's K times the quantity, A minus B plus 5C. So we can totally just pull that one out. And that's the end of the story, right? That's all we have to do. Yeah, Zaka.
For the formula T times the matrix ABCD,
This one,
is that given in?
this is given, yes. Yeah, where did this come from? I just literally made it up, right? Just the practice. Yeah, that's a good point. Okay, other questions? Brian,
D equals 0, right?
excuse me?
Does D equal 0?
Oh, in this case, it's not that D equals 0, it's the D just doesn't play a role. It just didn't show up in the formula. Yeah, so. Everybody good on this example? Let's try another one. Is that all right? I think I have time. Yeah, let's do one more example. Yeah, on Tuesday, I'll have to do a little more on this. At least getting it started today, but I will want to do a bit more on Tuesday. Not too much. This is the highlights of this section. It's just what is a linear transformation. But I want to do an example right now that basically, if this example I'm about to do was not true, we would not be sitting here right now because it would not make sense to put differential equations together with linear algebra, except for the fact that taking a derivative is linear. Taking derivatives you learned this in calculus actually, it respects addition and it respects scalar multiplication. Watch this. I'm excited. This is like the reason that this class exists. I mean, it's a big deal, right? So I'm going to define T to go, let's use P4 of R going to P3 of R. So this time my inputs are going to be from polynomials of degree 4 or less, and the outputs are going to be polynomials of degree 3 or less. And how is the formula going to go? I'm going to plug in P of X. And the output is going to be P prime of X. We're literally just going to take the derivative. Literally just going to take the derivative of that. Now, in this case, it's really not necessary. You might wonder, well, could I write it this way? I mean, why don't I have like my whole polynomial here? You could ask, well, why don't you just have the formula written in those terms? You could. I think we all could do this. Everybody knows how to take the derivative of a bunch of powers of X, right? This would be the formula if we wanted to write it all out. But which one would you rather work with? This or this? Guys, sometimes abstract is better, right? Simple abstract notation is cleaner. When I start verifying these axioms, it's going to be nicer for us to check it. So let's just check this one. So again, I would like to show that T is linear. One more time, practice this one more time today. And so for part A, I have to show that T respects addition. To check that T respects addition. So this time, on the first example, I had 2 by 2 matrices that I was writing out. Of course, I don't want to write my vectors as matrices now. So instead of using that notation, I'll use polynomial notation. Maybe P of X plus, what do you want to call the second polynomial?
Q of X.
Q of X. I love it. P of X plus Q of X. Something like that. Yeah. Okay. Now, the first step is to add these polynomials together. Now, if you had chosen to write it out this way, you would have a big step right there to do. You have to add up all the different powers of X, right? Term by term. But because I have written everything so abstractly, which I know annoys some people, right? Some people would rather see all the terms written out, right? But actually, because this is so abstract, these two things are already as added together as they're going to get, at least in this abstract notation. So I can view this as already good to go, right? I'm ready to actually transform that thing now. Can't really add them together any more than they're already added together here. So let's just go right into it. Let's just take our derivative right away. P of X plus Q of X. Put a big fat derivative on the end of that. Okay, so it's just the derivative of that whole big thing. But then what do you guys know that you can do with that? If you had sine of X plus e to the X, and you wanted to take the whole derivative of that whole thing, what would you be allowed to do? do them separately, right? You can, that's one of the properties of derivatives, right? Is that you can do them separately. I can do P prime of X and Q prime of X separately, and then add those together. And I can now see that I've pulled apart the P and the Q. This is literally just T of P of X, T of P of X, plus T of Q of X. Put our check mark there again. That's pretty much the whole thing. Where's my thing to erase the board with today? Move that.
It's right there. Next to the.
Oh, like the shirt?
Oh, the shirt, the eraser.
I'm looking for like, well, here's the eraser. What happened to my? It must be somewhere in the room. Anyway, I'll use this for now. It's fine. Is everybody good on this part? I don't know where it went. Okay, I'm gonna get rid of this. Okay, let's check that scalar multiplication works the same way. Remember, guys, what am I gonna put over here on the left side? It's what? There we go. Hey, I was like, this is like, some kind of a disappearing act. Okay, yeah, so there we go. We got that part. Part B, sorry, I'm going fast here, guys. T respects scalar multiplication. Right? This one, I take T of K times P of X. Again, I just immediately take the derivative of it. So I'm going to start off with the derivative of the whole thing there. What do you know about constants when you're doing derivatives? Pull them out, right? You've done that many times, I'm sure. So you pull that K right outside. It leaves you with just the derivative of P of X on the inside. And that's just simply K times T of P of X. Put another check mark. Again, we use nothing on the left side. We're leaving the left side blank. And we just write on the right side only. Make sense? Now, guys, not everything is linear, just so you know. Derivatives are, thankfully. Because derivatives are linear, we can combine differential equations and linear algebra into one course, and it makes a lot of sense to do that. Without that linearity property, we probably would not be here today in one Math 250B class. That we would have to do a separate thing for differential equations and a separate class for linear algebra. It wouldn't make sense to put them together if this wasn't true, that this is a linear transformation. Okay, so that's kind of nice that works out so that I at least have a job. By the way, though, but there are some surprises. Not everything is quite as linear as you might think, right? Let me just briefly, I want to go quickly on this. I could try to do something. I'm going to define T to go from Mn of R to R via T of A. So this time I'm not going to write out the entries of A. Again, I'm just going to call it capital A. Equals, I could do it this way. I could spit out the determinant of A. So we input a square matrix and the transformation takes its determinant. That seems like a very natural thing to do in a class like this. However, in this case, note T is not linear. It is actually not linear. Why not? Well, let's think about the addition for a second. If I had A plus B, again, on the polynomials example, I'm using P's and Q's, right? Because those are letters that go with polynomials. now that I'm back in the world of matrices, I'm using capital A, capital B. It's nice to use notation that fits the problem, right? Well, if I transform A plus B according to the formula, I'm supposed to just take the determinant of A plus B. And my question for you is that the same as, so down at the bottom, I would be hoping to end up with this, yeah? T of A plus T of B should be at the bottom, but if I think backwards for a minute, that's gonna be the determinant of A plus the determinant of B. Is this true? We actually saw that actually in the group work, I think, and probably also in the homework, right? Back in earlier in chapter 4, when we were looking at subspaces and stuff, it did not work. This is a not equals to right here, folks. This is a key surprise, is that determinants do not respect addition. You could get lucky, maybe a specific choice of an A and a B might work, but it's not always going to work. And because of that, determinants don't respect addition. So you can have examples that are not linear, such as this, and sometimes you get surprised by that. Okay, so that's a quick little, definition of linear transformation, along with a couple of examples. I have 1 minute to do 3 problems. I don't think so. I tell you what, would it be a good answer for me to address those problems if I, after my second class, just make a short video with the solutions to these? Would you watch it if I did it that way? Instead of trying to take 2 extra minutes and scramble right now, would that be better?
Yeah.
Okay, after, I won't be able to do it till like 5:30 tonight. Okay, so give me a couple hours. I will make a video 13, 18, and 21. I'm gonna do those on a video right after class today. Okay, and I'll send it out to you through the email. Okay, yeah, Kenny. Actually, yes, the T would respect the scalar multiplication, but it already, right, as soon as it's not respecting addition, it's already game over. Yeah, good point. All right, see you guys soon. Keep watching your emails this weekend. You never know what I'll have to surprise you with. 13, 18, and 21. I have to remember that. Yeah, have a good day, guys. Oh, thank you. No worries. The thing you don't want to do is leave it in your pocket when you go to do your laundry. Because I've had one of those things where it didn't have the cap on good, and then it goes in the laundry, it gets into the soap, and my whole load of laundry was like, that happened to me one time.
marker?
Huh?
Was it an Excel?
Yeah, it was one of these markers. I just had it in my pocket when I went home that night. I never took it out of my pocket. And then when I go to do my laundry, I didn't have the cap on it right. And so it was terrible. It ruined a whole load of my clothes.
You couldn't wash it again?
Not really. I mean, it was like all over everything. So it was, yeah, I kind of had to
That's a bummer.
get a bunch of new clothes at that point. Yeah, that was
Hopefully you
annoying.
needed some new clothes.
Yeah.
My mom always makes it every Monday.
She does?
See you, Don.
Wow, that's a super mom right there.
See you guys later. Bye.
Oh.